Well, hello everyone. My name is Vijay Rajkumar. I'm a computer science major, and I'd like to talk today about a project that I've been working on to improve immersion in virtual reality for real-world scenes and environments. Before I get started, I'd like to do a quick outline of what I'm going to be talking about today really quickly. The problem that when we're talking about content creation when it comes to virtual reality for real world environments, we're generally talking about, in terms of the content being created today, 360 content, and that is standing point content that you can't move around in. A few solutions that other people have done, what I've done, and really quickly after that, limitations and future work that can be done to improve this. But to talk about the problem, I believe it's most important to talk about, to address the dream, our goal. Pictured here is a scene from the famous film Citizen Kane. This is a fairly important scene where the central figure of this film has come to the realization that despite having acquired all of the material wealth in the world, he's lacking the thing that's most important, happiness. And it's really a tragic scene, as you can see from the reactions of the people, the staff who are in his mansion as they watch this tragic fall of this iconic figure. What I really would like is to be in this scene. I think it would be an incredibly more emotionally powerful experience if we could stand in the scene and walk around and inspect the reactions of the different characters. This is what people are calling cinematic virtual reality, and the fact is we are not there yet. But what we can do is build upon decades of research that has gone into virtual reality and telepresence, and specifically looking at advancements in the fields of graphics like texture mapping and in 3D computer vision like structure from motion and multi-view stereo for 3D reconstruction. I believe we can help bridge that gap for content creators to advance and get closer to that goal, even if we're just taking a tiny step forward towards that dream. So the goal of virtual reality is total immersion. And the reason why we're focusing on content acquisition today is because we can really break down visual immersive technology into 4 primary categories: tracking the motion of a user, image rendering, so actually creating the image that's then displayed into a user's headset, and then the display as well, which we want to have a wide field of view and high resolution display. Today, I mean, as of last year, really, consumers all over the world have access to these things through headsets like the Oculus Rift and the HTC Vive. The HTC Vive allows room scale tracking, meaning that we can actually walk around a room and feel like we're there. Sure, there are problems like a limited field of view still, and the fact that these headsets are tethered to a PC, but when we're talking about what we can be doing today, I think content acquisition is a real problem, because when we're talking about real-world scenes, these scenes are being captured with tools, with camera rigs that look like this. We have the Samsung Gear 360 camera, a GoPro Omni, and a Ricoh Theta, and these are all monoscopic 360 camera rigs. The production for these 360 content is great. A lot of really great talented producers making content. The distribution systems are great, YouTube and Facebook, but the problem arises when we look at what these 360 images are comprised of, which is simply, in the case of this GoPro Omni, six wide-angle images stitched together in a panorama, as we would stitch together any other panorama by finding correspondence points and then and stitching together the images based on their relative poses, and we get a spherical view because the shape of the camera rig. So this is what the scene would look like if you were wearing a headset. It looks great. The images are 12 megapixels each, But then you notice I can't tell how far away that rock is, or when I see that telescope there, I want to walk over there, but I don't have the ability to do that. So we need to introduce 3D geometry into this. And thankfully, there's been a lot of research that's gone into 3D geometry and reconstructing the 3D geometry of scenes. A few solutions. I'm going to go through these really quickly. Google Jump is Google's omnidirectional stereo camera system. It's not the only omnidirectional camera system, but the way that it works is it's 16 GoPros in a single rig, and there's enough overlap between each of these images, the images taken by these cameras, that we can triangulate points and extract depth for every pixel. Their algorithm then interpolates that 3D reconstruction so that you can move your head. You can look around and have a consistent view of the 3D geometry of the scene without holes or problems like that. But however, you can still move your head side to side, but you can't actually walk around the scene still. You do have a sense of depth, which is nice, but ultimately these cameras are very expensive and it requires specialized hardware. This paper, which came out earlier this year, tries to address this question. So the authors of this paper take a regular monoscopic camera rig like those that we were looking at earlier. They rotate the rig so that you get that overlap and you can extract depth information. Using that 3D data, they track the movements of a user's head and are able to warp that panoramic image so that the image the user sees corresponds with the movements of the user's head. Matterport is a commercial product intended for virtual tours, particularly for like real estate and things like that, and they also combine 3D reconstruction with 360 capture. We have however, they separate into two modes. You have the street view style mode, where you can stand in these beautiful high resolution panoramas, but teleport from point to point. And you also have the walkable mode. So if you're in an HTC Vive, you could walk around the 3D reconstruction that they capture with their camera rig, which captures both a panoramic image and also the 3D geometry of the scene with depth scanners that rotate around this rig. However, the image quality isn't great. It is pretty good though, but I believe that it is fine. My understanding is that it is fine-tuned manually in post-processing. So my solution, instead of thinking about 360 capture versus 3D reconstruction, let's combine the two so that when you're standing at the location of one of the rigs, you can get that beautiful high resolution, great image quality and look anywhere, but you also have the ability to walk around in the scene. You could be in your living room, but visit a museum like the Louvre in Paris and simultaneously appreciate the grand scale of the building and the rooms while appreciating the artistic detail of the paintings that you see. We could set markers around the room so that you know where you would be able to see these panoramic views, the images captured, the scenes captured by the 360 rigs, and hopefully when you're standing there you would see an improvement in image quality and a more consistent view. 3D reconstruction, I'm not going to go into too much detail about the differences between passive and active scanning, but the basic difference is that with active systems we're using time of flight sensors or real-time stereo sensors like the Kinect and the Kinect 2, and with passive scanning, we don't need any specialized technology. We're able to reconstruct the geometry of a scene or an object exclusively from RGB images. The standard passive pipeline that we use is structure from motion, multi-view stereo, and surface reconstruction. So structure from motion is one of the crowning achievements of 3D computer vision. an unstructured set of RGB images, we're able to extract the camera poses and the camera poses of each of the images used based on the correspondence points and triangulating these points. Once we have the poses of the cameras, we can extract the depth of every pixel in each image used with multi-view stereo, and thereby we get a depth map for every image that we've used. We fuse those depth maps together to get a dense point cloud, and using an algorithm like Poisson surface reconstruction, we can recover the 3D mesh of that object or scene. Now, we can't just put a spherical monoscopic panorama in a 3D space, because the transition between those two environments would be jarring. So what we do instead is we take the images we've used to construct the 3D panorama and map them to the 3D geometry. Texture mapping, by texture mapping these, we take each of those images and orthogonally map them to the faces of our 3D mesh without improving the image quality, without increasing the complexity of the geometry. So what I've done, taken a highly textured room and captured a 360 sphere, panorama sphere. Taking a number of images with my iPhone, I've created the reconstruction of the scene using the pipeline that the passive pipeline that I just talked about. And then taking the images from our 360 rig, which we register in that 3D space, so we get the poses of those 6 images from our GoPro rig in that same 3D space using the same structure from motion system. We then map those images orthogonally to our 3D geometry. So really quickly, so this is what the scene would look like in our 360 view. And this is what the scene looks like in our 3D reconstruction. And yes, this is not the greatest 3D reconstruction. The pipeline that I used was definitely not the is not the state of the art in terms of 3D reconstruction geometry. However, it is what I used to get the quality of texture mapping that you'll see in the next few slides. So this is me in the Vive walking around the 3D scene before improving the image quality with our 360 images. So this is what the scene looks like. You can see a table, an eye chart, and once we improve take our 360 images and map them to the scene, this is what we get. Here's a close-up. As you can notice, you can actually read down to the very bottom line of the eye chart. And finally, you can actually read the text. You can clearly see what the images in these newspapers are showing. And finally, our limitations. There's temporary limitations and a fundamental one. Our temporary limitations are that the geometry, as you saw, is not perfect. There are too many holes. Also, you may have noticed that the improved image quality did not map to the entire scene. That's because our GoPro images didn't successfully register with our not all of our 6 GoPros successfully registered with our structure from motion system. Now the fundamental problem, however, is that we aren't dealing with dynamic scenes. We're still dealing with static scenes. So if we wanted to walk down the halls of the scene I talked about earlier with Orson Welles, we would actually need people in the scene and capture their motion. Holoportation is a paper that came out of Microsoft Research a year ago, I think, 2016, and it does real-time motion capture. paper from our own department, temporally enhanced 3D capture of room-size dynamic scenes with commodity depth cameras, captures room-scale environments, static and semi-dynamic, or dynamic and semi-dynamic objects. So to conclude, I think what we've presented here is an interesting system, but there are clear, I think there are clear problems with the limitations with the implementation that I've taken so far, but I believe the work that needs to be done next is clear, and I think we are getting closer and closer to achieving that dream of being in the scene with Orson Welles, or being with being with those we love who are halfway across the world through virtual reality. Thank you.